Okay, next we're going to see a special case or a special situation that arises sometimes in structured proofs. Is a case where we want to have a transitive chain of reasoning. So you see that quite often in mathematics. You see these proofs that say A equals B because of something, equals C because of something else, equals D equals E, and therefore A equals E by transitivity of all of that. And sometimes it's not equality, sometimes it's inequalities, so greater thans or combinations of greater thans, equal, greater or equal, and so on. And then that's how the proof is structured, or sometimes just part of a bigger proof. And in Lean, there's a mechanism for doing that as well, and it's called calc. So it's a structured command, just like have and assume and fix and so on. And the syntax is, well, it's given here in a schematic form. I mean, the idea is simply you have left-hand side equals right-hand side, colon, proof. And then you write ... equals, and then you continue. So you need the ... Mathematicians don't have that to just continue by saying equal. There's kind of a blank here, if you like, in mathematics. And probably they would put these things, over there in the right margin. That would look more mathematical, but in my experience, when you develop larger proofs with more complicated sub-proofs, like here the byes are very short, but often you have bigger things, it's better to adopt exactly the style that I've done here, where you see the formulas here, they all line up nicely. The equals line up as well, and the proofs line up. It's still not very elegant, but you see what's going on, right? So what is this property here we've proved? Well, it's 2 times m plus n equals m plus n plus m. And we do it in 2 steps, right? We're like, well, 2 times m is, right, this here is the same as m plus m. And then you see, well, this is not in the right order. It's not the same order as that. And we use CC, because CC can do reasoning modulo AC, so associativity and commutativity. So that's a good match here. Whereas for 2 times m equals m plus m, well, this is a lemma in Lean. So you, in some sense, have to know it. So we're not at the point in the course where I would ask you to guess the name of this lemma, because I haven't even taught you, how to search, the library or anything. But the big part of theorem proving is to find the lemmas you need. Sometimes you just read the files, where, everything related to multiplication is, or everything related to, I don't know, sets is, and you just learn it. But there are also commands that help you find things, and so on. Right? So if you were to write this without calc, then it would be more painful, because you have to have intermediate labels here. You cannot use the ... syntax. You have to repeat the term. And at the end, you need to use transitivity explicitly, whereas here you get this for free, right? So that this equals that, that's what the whole proof stands for, and we can use it, as a proof of the lemma, which is the same thing. So we lose some clutter by using calc, but it's not a very, we're not going to use it very often in this course, so I'm not going to put much emphasis on it. What else do I want to say? Oh, here you see show. Here I was too lazy to repeat the goal, so I just wrote the show underscore. But I could, of course, have put this whole thing here. Okay, that was short, so we'll continue with the next block here. So far we've had, in lecture 2, backward reasoning with tactics, and lecture 3, forward reasoning with structured proofs and proof terms. Here we're going to see another, a third way of doing things, which is forward reasoning with tactics. And this is, very useful because, most of us use tactics as the default mode of operation in Lean. But then we miss once in a while the have and also the let, which I haven't introduced, but it's simply a mechanism to introduce a synonym, right? So C prime here is a synonym for C. It's just a definition. So similar to have, which is a lemma, but this is for data. This is for values. So yeah, so we have these haves and lets and so on in calc as well in structured mode. But yeah, Lean also provides commands that have the same name and more or less the same syntax. And especially have and let are useful, especially have, I would say. And once in a while, calculational proof maybe. So here you see, you can write have exactly like in structured proof, but in the middle of a tactic. You see, you have intro and then you have a have, right? And there's also a let here, which you know, has more or less the same syntax as the have. Yeah, that's pretty much all there is to it. Have is going to be very useful for debugging. So sometimes you want to apply something, you say apply this lemma and it doesn't work. And then you wonder, what does the lemma actually look like when I pass this and that arguments to it? You know, you want to show something. Well, the best way to show it is to give it a name and add it to your context, right? So here, you know, I want to see the result of HAB, HA, you know, it's supposed to be B, but I'm not sure. You can simply, you know, you don't know what it's going to give, right? So and then you look at the context and then it says, oh, HB is B. So that's quite informative, right? So that's a good debugging tool as well. And then you can remove it once you have, you know, extracted the information you wanted with the have. Okay, I'm not going to continue with the next section now because it's a big one coming. So see you in a moment.